Around 1 decade ago, the concept of Internet of Things started to gain some popularity. It's better. But, afterwards, the Internet of Things industry now is experiencing a massive growth with incredible 127 new devices being connected to the internet in every second. And this huge number of connected devices are continuously generate data and lead to a massive growth of data generation. And IDC estimates that in the global generated data from IoT devices will grow to 73 zettabytes, which around 40% of global data generation in the world. But the IoT is not the full story of data generation. Today, there are many other applications and services in the internet which continuously generates huge volumes of data. And the traditional database management systems and data processing systems cannot handle these volumes of data. So this challenge has led us to the big data era. And big data is basically the ways to deal with these huge volumes of data. And big data conceptually consists of three different V's. First, the volume, which means the amount of the challenge of the amount of data. And this fact that today the volume of data can be in terabytes or even petabytes. And second one is variety, which is the challenge of different types and formats of data. Data can be structured or unstructured. And the third one, velocity, which is the speed of generating data. And this fact that the data is generating at very high rate and need to be processed quickly after its production. So for solving this challenge, several large-scale big data processing frameworks have been designed and developed. Well, Hadoop, Spark, and Tez are some examples of these kind of frameworks, and they are mainly working based on batch processing paradigm. And batch processing is a store first, process later approach. It means that first, huge volumes of data are stored, and later in the second step, they will be processed. And these batch processing frameworks are inherently designed for processing large data sets that can take several hours or even days to be processed. So if we get back to the three V's of the big data, okay, we can skip the variety because variety is mainly an application issue. It's not so much a framework issue. But about the other two V's, we can say that the batch processing frameworks can satisfy the requirements of large volumes of data. However, they cannot handle high velocity of data. But there are some new application scenarios, such as IoT security cameras or financial transaction fraud detections. In these application scenarios, huge volumes of data are continuously generating and need to be processed at very low latency. For example, in fraud detection application, we want to block some critical transactions before they actually take place. So this challenge led to emerging of data stream processing systems or DSP systems. And in contrast with a batch paradigm, which is a store first, process later approach, data stream processing is an in-memory approach, which processes streams of data that are continuously generating at very low latency. And thanks to this property, if we get back to the three V's of big data, the data stream processing frameworks not only can handle volumes of data, but they also can handle the velocity of data. So data stream processing systems were originally designed to run on centralized clusters or in a cloud. Cloud has different advantages for DSPs. It provides scalable and elastic pool of resources and also increases the degree of system deployment flexibility for DSP applications. However, cloud also has some limitations for running DSPs, especially about the IoT devices. Well, the IoT devices, or in general, data sources, are located far from the data center servers, cloud data center servers. And they are geographically distributed at the edge of the internet and transferring large volumes of data to the cloud data centers via a long distance links. And these long distance links, make it impossible to process data at very low latency. And this challenge has led to a paradigm shift of the deployment of DSP applications into the geographically distributed computing infrastructures, such as fog or edge computing infrastructures. And these infrastructures bridge the gap between the cloud and end users and bring the applications closer to the main sources of data. And in this way, they reduce the necessary data transfer via the long distance links. And fog computing is one of these infrastructures. Fog, initiated by Cisco and later was standardized by Open Fog Consortium in an IEEE standard. And the main difference between the fog and cloud is about the resources that are used by these two computing paradigms. Okay, let's have a deeper look at the data stream processing application. Well, DSP frameworks are typically use a workflow approach. It allows developers to express the applications as a directed acyclic graph of the data transformations, which are called operators. And the operators are connected to each other by data streams. And every operator encapsulates a certain streaming logic and apply it on every incoming data stream item. Okay, now let's imagine what happens if the incoming workload increases. So at some point, some operator cannot handle the incoming workload. And they start to buffering the incoming data, and consequently, we will start losing the velocity. There is a standard definition here for the throughput of those overloaded operators, which is called maximum sustainable throughput, or MST. And MST means the maximum throughput of a specific operator with a given configuration to that operator. And the typical solution for solving this challenge is the prioritization or replication of those operators which cannot manage to process faster. And the DSP frameworks are responsible of doing these kind of optimizations. And in the last figure, you can see a high-level architecture of a DSP framework. And here, the Apache Flink. And Apache Flink is one of the most popular DSP frameworks, which we have used it in our experiments. So you can see that there is a client component, a job manager component, and multiple task managers. And these task managers are where the operators are deployed. So in this way, we deploy the application, the DSP application, into the DSP framework. But in the next step, we also should deploy the DSP framework into the computing environment. About the centralized computing environments, so we have multiple machines, and the task managers, which are below the operators, are distributed on the machines. And every machine can be a virtual machine, a physical machine, or containers. But what about the geo-distributed environments? Well, let's assume we have deployed a fog computing infrastructure here in RAM. So every computing node is located in a different location. And if we are going to deploy the DSP application into these environments, we have this opportunity and also this challenge to where to place each operator. Okay, so we saw that deploying of DSP applications into the geo-distributed environments has some advantage for the deployment of DSPs. The most important one is that the computing nodes are located at the edge of the network. So when we deploy the application, it reduces the volume of necessary data transfer via long distance links. However, in contrast of the cloud, the geo-distributed infrastructures have strong constraints in terms of the resources. First, scarcity. Well, the number of resources which are available in a specific location is limited. Second, availability. Well, the geo-distributed machines may have greater failure rates than regular data center servers. And the most important one, heterogeneity. The computing nodes are geographically distributed in the environments and experiencing heterogeneous communication delays to other nodes. So, although the deployment of DSP applications into the geo-distributed environments is better choice, however, there are some challenges in terms of resources, and we can say there are two main challenges here. First, heterogeneity of network latencies. So I told you that the operators need to deploy on the computing nodes, which are geographically distributed and experiencing heterogeneous communication delays. And the second one, non-stationary workloads. Well, many of IoT applications during runtime and generating processing data streams experience unpredictable workload variations. So we define the objective of this thesis as addressing the problem of resource management for data stream processing in geo-distributed environments. We consider three different sub-challenges in this context. First, the impact of large and heterogeneous network latencies among the nodes on the DSP performance. Second, the impact of non-stationary properties of incoming workload on the resource allocation. And third, the lack of a real and publicly available fog or edge computing platform and its impact on realistic research and development of DSP applications and DSP systems. So we follow a specific approach in this thesis. We redefine the objective to address those sub-challenges and having contributions in them. And we redefine the objective as maintaining the system throughput such that process incoming data with no undue delay. We know that the throughput in general means the rate of the processing or production in a system. And if we get back to the velocity means in the big data, velocity is the fact that the data must process quickly after its production. So we focus on throughput, and in this way, we try to address the challenge of velocity in big data. And because our focus is on throughput, we can manage every operator separately. We know that if each operator does not produce congestion, then the whole workflow will work correctly. And it will simplify the resource allocation and also the rescaling or automatic scaling in the system. And because the rescaling approach focuses on every operator one by one, so for controlling the DSP performance of the DSP application, of an application, we can only focus on the performance of the operator one by one. And you see, it will also reduce the problem complexity. So we have three contributions in this thesis. The first research question was how to estimate the performance of a DSP application when different reconfigurations or different system changes happen in the system. And our contribution is a mathematical performance model for geo-distributed stream processing application, which is derived from and validated by extensive experimental measurements. And the second research question was how to continuously adapt the system configurations during those changes, like changing the workload or the availability of nodes. And our contribution is a resource auto-scaler which guarantees the DSP maintains or provides a sufficient throughput during runtime. And the third question was how to continuously monitor different system metrics as different metrics in the system and experimentally evaluate any potential solution in these environments. And our contribution is the design and development of a general fog computing testbed for the DSP applications. So in the following, I will present the first two contributions, and because of time limitation, I refer you to the thesis for the third one. Okay, now let's have a look at state of the art of the two first contributions. Well, there is a lot of proposed works about the DSP performance in the literature. Well, they can mainly categorize based on three dimensions. First, some of the works proposed for centralized environments, while some others proposed for geo-distributed environments. And they are also varied about the QS objective that they try to estimate. That can be throughput, latency, cost, or a combination of them, and so on. And the third one is the methodology that they use for this purpose. So these works are useful because they help to better understanding the DSP performance. However, first, there is a lack of realistic evaluation and realistic modeling in a real environment, and also lack of experimentally validated knowledge about the DSP performance. And second, most of these works propose for a specific optimization techniques, for example, for operator placement. And these works typically try to show the quality of the proposed model in comparison with some chosen baselines, and they do not necessarily establish the accuracy of the model itself compared to a ground truth. And in contrast to the proposed models and works, we will present the performance model as our first contribution, which you can see its position in the tables. And this model is derived from and validated by extensive experimental measurements, which allows us to clearly evaluate the prediction accuracies of the model. So there is similar categorization for data stream processing autoscalers. Again, they can be categorized, some of them proposed for centralized environments and some others for geo-distributed environments. And and about the QS objective, they use different QS objectives like throughput, cost, or latency, and so on. But the most distinguishing element is the strategy that they use to come to their rescaling decisions that can be threshold-based, learning-based, or model-based. Well, the threshold-based solutions facilitate scaling decisions. However, finding a proper threshold or a set of thresholds which works for a wide range of applications and different states of the geo-distributed environments can be very difficult. And learning-based approach do not need the thresholds. However, they must be trained potentially for a long time to have accurate rescaling decisions. A model-based approach have not these drawbacks, And the only challenge is finding the proper model. So we will see as the second contribution, which you can see is positioned in the table, we will see that we propose an autoscaler, a DSP autoscaler, which the only one that use the model-based strategy and also throughput as the QS objective, and we will see how it performs a threshold-based baseline. So the first contribution, the performance model. Okay, let me first review the challenge. And the challenge here was understanding the DSP performance in geo-distributed environments. And we know that any configuration decisions, like the replication of the operators or the different changing the placement of the operators and so on, can have a significant impact of the DSP performance, the overall performance. So we propose a performance model for data stream processing in specifically for fog computing environments, which is derived from and validated by extensive experimental measurements. Okay, before talking about the model, let me first describe our experimental setup. Well, for this contribution, we used a 32-core server, and we run 16 computing nodes on that server. We also used some emulated network latencies among the nodes, among the computing nodes, and we used Apache Flink as the DSP framework, and we run Apache Flink on top of the nodes. And our focus is one operator at a time. And the operator is connected to a upstream operator and downstream operator, which are source and sink. And the operator itself can be replicated, and the replicas can have different heterogeneous network latencies to other nodes. And we used a 100,000 tuple 2 records as the input stream. And also we used a fixed execution inside the operators and the replicas. And this execution is applied on every incoming data stream. And in this way, we can tune the computation complexity of the operators. So you can see an example of our experiments in this curve. And it is clear that when the number of replicas increase, the processing capacity will increase, and consequently, the processing time will decrease. But you can see that there is a fluctuation in the curve. And this fluctuation comes from the network latency. It means that when we add a new replica to the system, it has its own network latency to the other nodes. And this network latency has an influence on the overall performance. So we are going to model this situation based on those parameters, like the number of replicas and the network latencies and so on. But in the first step, we focus on the most important parameter, which is the number of replicas. So we know that, and in this curve, in this chart, it's also clear that when we increase the number of replicas to n, the processing time will decrease proportionally by n. So we have a 1/n curve, and we can use it as the first version of model, and we also add an alpha parameter to this model as the computation capacity of a single node. And now, based on the one measurement in the system, we can get the value of alpha, and then we can predict the rest of the points. And you can see in the chart, you can see the difference between the curve of predicted values and the actual values. So there is a difference between them. So yes, we have the first version of model, but its accuracy is not good enough. So in the second step, we also try to add the network latency to the model. We know that if we spend more time in the network, the system execution will be slower. But we found that among different network latencies of different replicas, the most important one is the greatest one. And this is the one that determines the overall performance of the system. So we added ND max or maximum network delay to the model. We also add a gamma parameter has the impact of network delay on the overall performance. So now, based on two measurements, we can get the values of alpha and gamma, and then we can predict the rest of the points. And you can see the difference between the predicted values and the actual values in the chart. It's much better than the previous one. So we still try to improve it. We also found that there is a polarization inefficiency when we increase the number of replicas in the system. So we added a beta parameter to the model as the polarization inefficiency of the DSP framework, and in our case of OpenChip. So now we have the complete model, and based on three measurements, we can get the values of alpha, beta, and gamma. And then if we predict the rest of the points, you can see that the result is better than the previous one. And the two curves even are not identical in some points. Okay, so I told you that for using the complete version of model, we need to have three measurements. But in many real situations, we only have the first one. But we saw that even with the first measurement, we can use a version of model. Its accuracy is not good enough, you can see in the chart, but at least we have something. But you can see that as soon as we have the second measurements, its accuracy improved to much better point. And when we increase the number of measurements to 4, the prediction accuracy is around 2% of the actual values. So let me summarize the first contribution. Well, the challenge was understanding the DSP performance in geo-distributed environments. And we proposed the performance model, which is backed by the experimental measurements and extensive experimental measurements and evaluations. And we saw that its accuracy is around 2% of the actual values. So as I told you, DSP applications experience workload variations and infrastructure change during runtime. So the system needs to be adapted with these variations. So in the next step, we try to propose an autoscaler which uses this performance model to issue its reconfiguration decisions. Okay, so second contribution, a model-based autoscaling. Well, let's first review the challenge. Well, I told you that many IoT applications which are generating and processing data streams experience variable amounts of incoming data. So the DSP system must be scaled up or scaled down based on these variations to maintain sufficient throughput. And the second is that the DSP application is not a monolithic entity. It's composed of multiple operators which need to be scaled up or scaled down individually. And the third challenge is that the geo-distributed environments, or specifically fog computing networks, are known to be heterogeneous. The computing nodes are geographically distributed. So when we deploy the DSP application in this environment, every operator can potentially experience different heterogeneity in network latencies to other nodes. So we propose Jscale, a geo-distributed stream autoscaler. And the main objective of Jscale is to providing a sufficient throughput while using no more resources than is strictly necessary. And the throughput here means the maximum sustainable throughput, or MST. And the main features of the Jscale is that first, it continuously monitors different parameters, different performance metrics, and workload in the system. It dynamically adds or removes operator replicas, and it relies on the proposed performance model. So this is the overall system design of the Jscale. Well, the figure is a little bit complicated, but essentially we have two layers or two parts in this figure. Well, the top layer is an implementation of Kubernetes and deployment of Flink on top of it. We use it Apache Flink as the DSP framework. We also use it Kubernetes because Kubernetes now is being used in many fog and edge computing scenarios. So we used it. And in bottom layer, you can see Jscale. And the core element, the main component of Jscale is an operator-level map-based autoscaler, which use map loop pattern or feedback loop pattern, which is the design basis of many self-adaptive systems, monitoring, analyze, plan, and execute loop pattern. And it collaborates with a model-based performance predictor, which predicts the MST of the given configuration. And once any resource configuration rescaling decisions has been made, the resource controller component is in charge of the implementing of that reconfiguration. So let me describe each phase separately. First, monitoring phase. Well, I told you that we need to have an up-to-date information about different metrics of the system. So Jscale regularly monitor different metrics, including incoming data rate, current throughput of every operator, and level of back pressure of the operators. And the second phase is analyzing phase. An analyze phase is in charge of deciding when a scale up or a scale down decision is necessary in the system. So I told you that the Jscale works based on the proposed performance model for having accurate predictions about the throughput objectives and so on. So when the system is overloaded, we know that we need, and we use back pressure to find this situation. And the percent of back pressure in the system shows that at least one operator is not sustaining its throughput. And for scaling down, we do not have to do the scaling down, but we do scale down when we can. It means that with fewer resources and less density, we can still support the current throughput. And the performance model is useful for these decisions. And the third phase is planning phase. And plan phase is in charge of identifying the new resource configuration which should be used to reach the throughput objectives, the performance objectives. And when an operator is overloaded, we know that we should add at least one additional resource units to that operator to increase its processing capacity. We, however, have no way to accurately determine the throughput objective that should be reached and to resolve the situation. We therefore, every time, add the number of resources, increase the number of resources by 1. And the performance model here is useful to choosing and selecting which resource unit should be added to the system. But for scaling down, the goal is that removing as many resource units as possible without reducing the MST below the current throughput. The performance model delivers us these estimations. And the last phase is execution phase. And execute phase is responsible for executing the reconfiguration decisions taken by plan phase. And there are two different challenges that need to be addressed here. First, properly providing an updated list of resources for Flink. Well, for scaling up, the system chooses the resource with lowest network latency to others. And for scaling down, it selects the resources with greatest network latencies to other nodes. And then it should make a change, should trigger Flink to make a change in its execution model. So for evaluation purpose, we use a Testbed. And Testbed is our third contribution in this thesis, which I'm not going to talk about it here and refer you to the thesis. where we have a complete chapter about it. But we used it as the testbed platform. And here you can see its diagram. We use 10 Raspberry Pis as the computing nodes, and then we set up Kubernetes on top of them, and then we deploy Apache Flink together with some other tools like Prometheus, Grafana, Kafka on top of Kubernetes. And in this figure, you can see how we deploy different tools and also Jscale on different nodes. And for the workload, we used the famous New York City taxi ride datasets. And for the application is simple, but is useful enough. And it is the calculation of Euclidean distance between the pickup locations of the taxis and 3 different tourist hotspots in the New York. And for the baselines, we used 3 baselines to compare with the Jscale and showing and evaluating the performance of Jscale. But here I only mentioned the first one, which is a threshold-based baseline, which use CPU utilization and monitor CPU utilization. And every time it adds or removes 1 resource unit to the system, and because it's network latency unaware, so it just selects the resource out of an unsorted list of resources. And for evaluating the performance of Jscale, we use different metrics, a variety of metrics, some metrics from a spec cloud working group like accuracy and time share, and some more popular metrics such as number of reconfigurations and number of resources. And here, again, I only showed 2 charts of the comparison between the Jscale and that baseline. And in the top chart, you can see the red line is the workload, and the blue bars are the throughputs of the 2 autoscalers. And you can see that the left one, which is the baseline, rescale the system more often. And the bottom chart shows the number of replicas used by the 2 autoscalers. And again, you can see that the baseline uses more replicas. So orally, we can say that Jscale has 52% fewer resource reconfiguration and 17% lower resource usage than the baseline, while in a similar time, it can process 22% more data than the baseline. So let me summarize the second contribution. Well, I told you about the necessity of resource adaptation in DSP systems when the different environment or workload characteristic change. And the challenge here was when and how to rescale the system. So we proposed a Jscale, and Jscale used a MAVE-based pattern, and also bases its decision on the proposed performance model. And we saw that how Jscale produced fewer resource configuration and processed more data than the baseline while using fewer resources. So let me conclude the presentation. Well, I told you that many IoT applications that use and run DSP applications in the cloud environments face the challenge of long distance communication between the data sources and the cloud data center servers. And I mentioned that the community is transitioning of the deployment of DSP applications into the geographically distributed computing infrastructures. And we saw that because of the heterogeneous network latencies challenge, and also combined with the unpredictable workload variations, the resource management in these environments is challenging. So we had 3 contributions. First, a DSP performance model. Second, a DSP resource autoscaler. And third, a general fog computing testbed, which is augmented with some additional components for evaluating DSP applications. And for concluding remarks, I should mention that our contribution to resource management of geo-distributed environments make them better suited for running data stream processing applications. And we published the first two contributions in two different paper and in two conferences. The first one in the SAC conference and the second one in the ICCCN conference. And we also developed three different tools during this thesis. Jscale, which is Geo-Distributed stream processing, benchmarking, and performance modeling. Jscale, which is the Geo-Distributed stream processing autoscaler. And testbed, which is Geo-Distributed streaming testbed. And all of them are publicly available. And the contributions that have been made during this thesis can be followed by four different directions. First, we did not consider stateful operators in our contributions. Well, statefulness imposes some additional complexity, especially for optimization techniques, like the number of the replication and the operator placement techniques. And the general tendency, especially for autoscaling systems, is using state migration protocols to manage these states. However, using these protocols will add some additional optimization dimension to the system, which is the minimizing the number of state migrations in the system. And the second one is that I told you about the heterogeneity of the network latency among the computing nodes. But similar heterogeneity also can be considered for other characteristics of the computing nodes, such as the processing capacity, the storage capacity, bandwidth, and different parameters. And if we consider these characteristics, these heterogeneous characteristics, so we can cover many other computing nodes, from gateways to network switches to set-top boxes, and also some special hardware accelerators, which are proposed for some specific applications and using CPU, GPU, or FPGAs as hardware accelerators. So we can cover all of these computing nodes. However, using these heterogeneous computing devices will raise some challenging questions. For example, how we can deploy the DSP frameworks in these heterogeneous nodes onto these nodes, or how we can model the DSP performance in these heterogeneous environments, how we can manage the resources. And the third one is that fog and edge computing infrastructures follow the advancement of cloud computing. So resource sharing models and federation of different fog and edge infrastructures are expected. However, in these kind of federated fog or edge infrastructures, well, the resources are provided by different providers. And the providers follow different regulations and policies. So the resources and especially users' context, such as their identity, activity, their location, and so on, should also be considered in the process of resource provisioning. And the last one is that any public implementation of a fog computing infrastructure should have the capability of connecting to a public or private cloud. And setting up this cloud fog continuum will enable the users to use and deploy the cloud for deploying their applications, partially or completely in the cloud. However, it makes it necessary to explore new coordinated approaches for resource management, for the application deployment in these cloud fog continuum. And that's it. Thank you very much for your attention. And we can start question and answer session.
Thank you very much, Hamid, and thank you for holding very precisely the time. So we'll now move on to the questions, and I realize I forgot to introduce the panel in which you're defending your PhD. So the panel is made of your two reviewers, so Laurent Lefebvre, who is a scientist at INRIA, chargé de recherche, Romain Rouvois, who is a professor at University of Lille. And then you have three examiners. So Professor Valeria Cardellini, who is a professor at the University of Rome, Tor Vergata. Cedric Tedeschi, who is associate professor, so maître de conférence at the University of Rennes, and myself, the chair of the panel, professor at the University of Rennes. And then your thesis director, Guillaume Pierre, who is professor at the University of Rennes, and your two co-directors are Professor Eric Emroth, who is professor at Umea University, and Dr. Johan Thompson, who is associate professor also at Umea University. So the tradition is to start with your reviewers, and I've just checked on the OpenStreetMap that I think Lyon is just a little bit further than Lille. So we'll start with Laurent. Laurent, over to you for your questions.
Okay, thank you for choosing this metric of fairness. Okay, thank you, Hamidreza, for your presentation, which was very clear. I also enjoyed a lot the manuscript, your report, your PhD document, which was very nice to read. I think with your work, we are a little less in the fog, but more and more in the sun. So I really enjoyed that. I have a few questions, Hamidreza. So in one of your first slides, you show an illustrative figure of Rennes, showing a fog infrastructure over Rennes city, which is very, very nice. Yes, this one. So here in such kind of scenario, latency between operators can be very small. Also, latency between source and sink can be very small. Do you see some realistic scenario that can be applied on such very small infrastructure? So Geoscale small infrastructure?
Okay. Okay, thank you for your question. So your question is that in this scenario, because I told you that let's assume that we deploy the fog in Rennes. Yeah. So the size of the city is small, so the distance between the computing nodes is not large, so the communication delay is small. And it cannot be realistic. Yes, it was your question.
Yes, exactly. Yeah.
Yes, exactly. As I mentioned, it's an assumption, and we didn't really deploy the fog here. I think I have a backup slide to show about the what exactly we said and we considered in the first contribution. Yeah, here. Yes, actually, we considered for the first contribution, we considered different capital cities in Europe and the communication delays between the different every pair of the capital cities. So we had a matrix of the network latencies among the capital cities, and then we used this as the static or fixed matrix of the network latencies in the systems. So it's still in some cases are not a lot, but it was more realistic, I think.
Okay, thank you. Okay, so concerning your performance model and estimation model, I see in the manuscript that you consider the K-by operator, which was not presented today. Okay, how do you deal with the fact that in some of the scenario, data volume reduce when we cross each operator, because each operator will do a filtering operation, a processing operation, and so the output data will be smaller than the input data. How do you take that into account in your performance model?
Okay, so your question, if I understood well, is that, okay, we considered, I didn't mention here, but yes, in the manuscript, I mentioned that we consider key by operator also in our experiments, and also we try to model it your question is that okay, how we can manage this fact that different in some applications, different operators and keyed operators or different replicas can have different loads to process. Yes.
Yes, and the output loads are smaller. Yeah. Mm-hmm.
Yes, I got the point. Actually, well, okay. First, about the keyby, if I find it, yes. Here, yes, I think here I mentioned in the graph, we can see that we have, this is exactly the experiments that we have, and you have seen it in the manuscript. And here we can see that we put the keyby close to the upstream operator, which is the map operator. And the reason is that the keyby is not, it's actually, I can say that it's a logical operator. It's not a physical operator. So as you mentioned, it's just try to filter the incoming data. However, we didn't consider these specific applications in our solutions. Yes, actually, we didn't consider the different loads. We considered that, okay, the incoming load is well balanced, okay? And in that situation, so we have keyby, but the keyby has not a strong effect on the performance, you know. And in the manuscript, I think we described this situation. I think it's an application issue. I can say it's an application issue or framework issue, the DSP framework issue to handle these different loads, but we didn't consider. And to be honest, I think it's not a limitation in our work. Yes, we worked on keybyte, but we just considered the well-balanced incoming load.
Okay, thank you. So if I understand well, the metrics that you use are focused on performance. But I think performance should be not only considered, we should also consider efficiency, and especially what about energy efficiency that you could link on energy metrics that you could use with this model? Do you think it can be applied?
So your question is that, okay, we consider some parameters in the model, and is it possible, for example, add an additional parameter like energy efficiency or, I don't know, consumption and these things in the model?
Yes, exactly. Yeah.
Okay. Well, it could be a solution. Actually, first, I should say that it goes beyond of the contributions of our work, and it's not out of our scope. But yes, why not? First, I should say that, yes, I think we can say that about the energy. It depends on you are going to consider it in the performance model or auto scaling. Because in auto scaling, the auto scaling itself, I think, is an energy efficiency approach in comparing with a static approach. I mean, just dedicating, allocating static configuration to the system. So when we do the auto scaling, it means that at any time we use the resources exactly as much as that is necessary. The system really needs. So I think it's in the nature of the auto scaling, there is an efficiency in energy consumption. This is about the auto scaling. What about the performance model? Yes, I think, for example, we consider different the heterogeneous network latencies among the nodes. It means that every specific resource that we use has its own network latency as a characteristic. So we can also say that it has its own network energy consumption or power consumption in general as another characteristic. So yes, I think we can also consider it in the model as an additional parameter. And I also can add to my words, I also can add this point that, well, in the, you know, energy efficiency, I believe that it can also be, I'll just try to speculating, it also can be considered in the placement. I mean,
Sure.
in auto-scaling approach, I mentioned that, okay, we have different steps, and in one step, we need to choose the resource that it kind of scheduling. I mean, we need to choose the resource that we are going to deploy the new replica, or more technical, the new pod on it in Kubernetes. Okay, so there I can show. I think I have one slide about it. Let me. Yes, here you can see that we designed and developed a specific a customized Kubernetes scheduler based on our proposals. And here we use a two-step scheduling. First, we filtered the available nodes, and then we prioritize or score the remaining nodes. And here in scoring, we again use the network latency for scheduling, and then we sort the nodes based on the scores, and then select the most the node with the most score. So here, instead of the network latency, we can also, for example, consider the power consumption, or I don't know, energy consumption as the priority parameter that we consider in scoring. So in this way, even in the scheduler, we also can use energy efficiency, I think. Yeah, but it's just kind of brainstorming.
Yes, you're right. Taking into account energy provisioning as a heterogeneous parameter can be very important. So I have two more questions, if the president let me in. So opposite to this question of energy, if I understand well, your autoscaler tried to find some fairness in terms of provisioning replica à la TCP, for me, à la TCP. So you have a scale up of one replica at a time and a scale down of several replica at a time. Could it be possible to have something a little more aggressive in terms of resources, where you try to scale up more resources than one at a time, because it needs some reconfiguration and it can have some cost, some delay, some QoS impact. So do you think a scale up more aggressive could make sense with a little pool of over dimensioning?
Okay. Yes, if I understood well. So your question is that, yes, in scale up, we only add increase the number of resource units by one.
Yes.
So it is possible to, for example, every time add more than one resources in scale up. Yes. Okay. So yes, actually, the short answer is yes. It was actually, to be honest, it was in our to-do list. We found it this idea actually after completing the second contributions, and we had this in our to-do list to do this and to have some experimentations about it, because we have seen it in a couple of other works, autoscaler works, papers that they use similar idea. And yes, because in scaling down, especially, we can remove multiple resources together. So if we rescale for scaling up, we add multiple resources together. So we have one configuration here, and then because of thanks to the model, we can remove multiple resources, and then we can tune better the number of resources in the system. Yes, actually, I believe it's really good idea, but as I told you, we didn't have enough time in this during the thesis, especially because we finished the second contribution, and then we thought about this solution. So we couldn't have some experimentation to experimentally prove that yes, it could be works better than the current configuration and current methodology. But yes, I believe that the idea can theoretically can have better decisions and less reconfigurations.
Thank you, Hamid. I think I understand. I have one last question concerning your future direction about stateful operators. I think dealing with stateful operators is very important, but it can add a lot of complexity. You need to orchestrate, you need to migrate the state. Do you think that dealing with stateful operators could change the number of operators we can deploy in a fog environment? Because if you have a lot of replicas, a lot of operators, dealing with the state can be a nightmare. So do you think dealing with stateful operators can change the way we do fog deployment?
The fog deployment.
Yes, the deployment of operators in fog, deployment of operators in fog.
The stateful operators.
Yeah.
Oh, okay. Yes. Okay. Your question is about the stateful operators. So yes, actually, as I mentioned in the future direction, the trending solution is using state migration protocols, especially for auto-scaling systems. I have seen some papers that have done it. Well, about the stateful operators, first, I think we can talk in two different dimensions. First, the state and handling and managing the state itself is one of the responsibilities of the DSP framework. I mean, the DSP frameworks typically do kind of state management and even state migration and for fault tolerance capability, which most of the new DSP frameworks have this capability. I mean, they are fault tolerance, and especially in our case, Apache Flink is fault tolerance. So they have some mechanism to manage the states. And yes, for example, some of the resources or in the DSP frameworks, the task managers are killed for any reason or failed. So the DSP framework has, or Apache Flink has some mechanisms to cover this situation or to handle the statefulness, keep the application. And so, yes, so the first dimension is that these kind of capabilities is the responsibility of the fog of the DSP frameworks. So no matter where you deploy the application, it can be a centralized cluster or in a fog. When you use a DSP framework, it has its own capability and responsibility to support these situations, okay? And this, but in the second dimension, I can also mention that the statefulness add an additional dimension also to the network latencies and the communication between the replicas. I mean, okay, when we talk about the one stateful operator, it means that there are different replicas of that operator also save their states, keep their states. So when you change the configuration of that operator, it means that you need also consider and manage these states. And when you run your system, deploy your system in a geo-distributed environments, so again, we have some more failure rate than the regular, let's say, cloud deployment. So it's make it more critical to handling these kind of state actually management mechanisms. So yes, I told you, but I think say that it can be a specific challenge for geo-distributed environments based on the heterogeneity that they have. The statefulness is not a specific challenge only for these infrastructures. I would say this. Yeah.
Thank you, Hamidreza. Thank you very much. It's all for me. Thanks.
Thank you very much, Laurent. So we'll move to the second reviewer, who is Professor Romain Roy. So Romain, over to you.
Thank you. So thank you for the presentation. It was a very nice presentation, very clear. I also agree with Laurent that the manuscript was nice to read. Pretty good state of the art of the literature, and it was a well-organized document. So thank you for this work. I also have a few questions. So definitely, I agree with Laurent that efficiency is also something that needs to be taken more and more into account. And you mentioned actually in your future direction, in your perspective, that actually you should consider more heterogeneous computing nodes. And I was wondering actually what will be the impact for your modeling approach actually if you had to consider more and more computing nodes?
Well, okay, yes. So your question that in our case, the proposed performance model, how this heterogeneity can have an effect of this to the system, yes?
Yeah.
Okay. Well, I didn't mention here, but in the manuscript we extensively talked about it. That, for example, we considered heterogeneity between the computing nodes and among the computing nodes. However, the computing node itself that we considered in our experiments are similar together. I mean, they are homogeneous computing nodes. So we don't have this kind of heterogeneity in the computing node that we use it in our experimentations. And the only heterogeneity that we considered was the network latency between them. Okay, so if we change this, I mentioned that there are some challenging questions here. The first one is the deployment of the framework itself, because for running any experiments, doing experiments, or running a DSP application in this heterogeneous environment, you first need to deploy the DSP framework itself. However, it is really challenging because even when we use it, when we deploy the DSP frameworks on the Raspberry Pis, we had many challenges and many problems and difficulty to do this. So when you change the architecture of the hardware and use different computing nodes with different architectures, the deployment and the implementation of the DSP itself, it can be very challenging. Okay. And the second is that, okay, now you have different computing nodes, for example, with different capacities of processing capacity. Okay, so processing capacity, I mentioned that can be another heterogeneity characteristic. But if the computing nodes have heterogeneous processing capacity, so their processing capacity will affect the throughput that they have. So, for example, if we add a new replica to the system, you also need, we consider the heterogeneity of the network latency in the model. But if the processing capacity also is different, so we also need to consider the processing capacity as another parameter to the model, because we are going to select another node for deploying the new replica, or to select another node for removing from the system. Okay, and now the processing capacity is an additional parameter, an additional value in the model that we must consider also in the model, and also in auto-scaling, both of them. Yes, and other characteristics in the same way. I mean, the different and heterogeneous characteristics in the computing nodes will increase the parameters that we should consider in the performance model and later in the auto-scaling.
Yeah. So yeah, so there were to me two issues basically. How do you explore this modeling performance, and how do you consider the wide diversity of devices that you will certainly integrate into your system? And if you have more and more diverse devices that you need to include into your system as part of your reasoning, there is also an issue of scalability of the approach, because maybe today you are considering a few tens of devices, but tomorrow, if you consider a wider diversity of devices, and the Internet of Things is the idea of having a very wide number of devices, then how do you foresee that your approach will scale with this huge number of opportunities when it comes to scaling up and down the operators?
Okay, so your question, if I understood well, is that, okay, if we try to have some experimentation on a bigger scale and larger scale of the nodes, okay, well, not exactly, because I would say yes. To be honest, I believe that it's a limitation of this work. And why we decided, because we have we had different choices for using as the infrastructure. For example, you know about the grid 5000 in France, and we had this choice and some other choices for using and experimenting on it. But for different reasons, we decided to use a cluster of computing nodes, the small computing nodes like Raspberry Pis. For different reasons, we chose it. Actually, we had some actually scenarios in our project, and also in the system we tried to the scenario was like this. Okay, in the fog, the computing nodes are not very powerful servers in like what we have in a data center server. They are usually and typically some small scale servers or with low processing power and storage capacity and these things. So we use Raspberry Pis based on this fact that they are much closer to real, let's say, real computing nodes in fog. I told you, I mentioned that, for example, gateway, network switch, and so on can be potentially a computing nodes. So we decided to use these kind of devices in as our computing infrastructure. However, when you use, for example, Raspberry Pi, okay, you can use 10 of them, you can use 20 of them, but it's not possible, at least for us, to use, for example, 500 of them. And yes, I think it can add an additional limitation to the system, which is the having experiments on high and large scale of the infrastructure. Yes, I believe we could do this, but it was our choice to use these kind of devices.
Okay. My next question is about the applications that you use as part of your validation. Can you summarize a number of applications that you consider as part of this validation?
The number of applications, your question is that which kind of applications we use it? Okay. Well, actually, I mentioned a couple of applications during the presentation. But yes, first, I should say that our work had a focus on the operator level, not on the application level. I mentioned that, okay, in every time we focus on one operator, and because we our focus on the is on the throughput as the performance objective, so we can do it. We can focus on every single operator separately and try to rescale it, to manage its performance to better works, and improve and maintain its throughput. So when you work on the operator level, you just focus on the operators and different types of operators. But of course, yes, when you are in application level, you try to have experimentations with different types of application, different size of applications, and so on. But in our case, we're focusing on the operators itself. And yes, for example, the operators can be collaborated and can be used in different types of applications. But this is my first point. And the second point is that the potential applications that we can consider can have or should have some characteristics. For example, I mentioned that the workload, the incoming workload, I mean the system when produce or generate the data, this data and this workload of data is very variable. I mean, during time it changes. So this is a characteristic of the application that we can consider. And the second one is that, okay, the infrastructure is geographically distributed, but the application itself, I mentioned several times during the presentation that our focus is on IoT applications, and usually the IoT applications in IoT applications, the data, the devices or data sources also are geographically distributed. So it can be also a second characteristic of the potential application for these contributions. And the third one is that, okay, the heterogeneity that we have among the, sorry, yes, the heterogeneity that we have among the computing nodes and consequently among the operators.
Okay.
Yeah, sorry. Thanks. So yes, as I mentioned, we can consider every application with these characteristics as a potential application for this work. And I mentioned that, for example, IoT security cameras or any other, or camera, for example, surveillance cameras or security cameras and these kind of cameras, or for example, some kind of, let's say, video broadcasting in a match or in a race, that are some new applications in fog and also in IoT. So in these kind of applications that we have some video streams, and the video stream come from the geo-distributed data sources, can be potential applications, for example, for these works. And so on. Yeah.
Okay, but my actual question was based on your experience with this application. Would you formulate some recommendation to the developers of this application to make your life easier as a manager of the system and make sure that the system can better scale, basically depending on the workloads? Is there any recommendation towards the developer to make the deployment and the management of this application much more efficient?
Okay. So your question is that how we can, for example, have some recommendations for the developers to better manage their application in these environments, yes?
Yes.
Okay. So actually, in the thesis, we didn't work on it. I told you, I mentioned that because our main focus was on the operators. But now I can have some speculating. For example, I think in the application level, when as a developer, when you develop your and you express your application as a graph, so you have this possibility to use different operators, and sometimes you can change some parts of the operators, some of your application. But again, in auto scaling itself and in performance modeling, there are, I think there is no thing that all the developers can do for this. I believe that most of these kind of optimizations and these kind of performance improvements are in very backend of the system. I mean, yes, for example, about if you ask me about some recommendations for DSP framework developers, yes, of course, they can add some capabilities or some kind of optimizations in their systems. But this is about the authors and the programmers of the DSP framework, not the application. So I think I should think about it more, and I would need to read about it, to study about it before answering. But right now, I believe that no, we don't have many recommendations for the application developers.
Okay. And my very last question before giving the hand to the others, member of the jury, is okay. So you define this performance model that you use for your scaling purpose. But did you consider actually at some point of checking the relevance of this performance model at runtime and eventually recalibrating the performance model because you observe that you diverge from what was expected, and you can somehow improve the quality of your configuration by adjusting your performance model at runtime?
I'm not sure if I understood your question well. So you mean that, okay, we evaluate and monitor the performance at runtime, or so if we have evaluate the performance with the final, I didn't get your point.
So far, what you did is that you have these performance models that you train and learn offline, a priori.
Okay.
And you use it at runtime actually to drive the reconfiguration process of your operators. Is that right? Okay.
For our case?
In your case, currently. But my point was whether you keep checking that your performance model is accurate at runtime.
Okay, yeah, I got the point. Yes, you mean that, okay, we do the performance checking and doing the performance modeling. The performance modeling itself is an online mechanism or offline mechanism, yes? And if we have tried to do it online, yes? It was your question?
Yes, I mean, you can do it offline, but make sure that during the online phase, actually, your performance model keeps being accurate, actually.
Yes. Actually, about the performance, actually, most of them for both the first and second contributions, we do every checking and every evaluating online. It's not an offline process. I mean, everything is online. We continuously monitor the resources and the throughput of the running system, and then based on these, the current situation and current state of the systems, we change the performance model. Not the performance itself, but the values, the values of the parameters during runtime, and then every time it decides about the new throughput objective, and or in auto scaling also. It's a runtime process. I mean, we don't have any offline process or pre-process before running the application. It works like this: start the application and start the measuring different parameters and monitoring different parameters. As soon as we have the first measurements, we can use the first version of model, the second measurement, second version, and third version, and so on. You know, we have regularly some measurements during runtime. And for example, about the auto scaling, everything is based on the current states of the system. For example, we monitor back pressure, and back pressure is an online parameter that the DSP framework itself provides for us. Or for example, we use the current throughput of the system, and current throughput also is an online parameter which we use them in the scaling and also performance modeling. So yes, I can say that even it can have some, it can affect somehow the quality of the performance, because as I mentioned at the beginning, and with the first measurements, we cannot use the full accurate and the complete model, but this is a drawback of the system. We need a few measurements to use a full accurate model, but we do it because we believe that during runtime, different conditions and different states of the systems of the replicas and operators will change. So we monitor them, and based on them, we calculate the throughput objective based on the model, and then doing the rescaling.
Okay, thank you.
You're welcome.
Thank you, Romain. So we'll now move to the examiners, and we'll start with the one who is furthest away. So Valeria, if you want to
yes,
ask your questions, the floor is yours.
yeah. So thanks, Hamidreza, for your nice presentation, and very clear also in the details. And I also appreciated the thesis. And I have some questions. Some other questions I had, you have already replied with the two previous colleagues. So my first questions regard the metrics that you have chosen for your work, because you consider the maximum sustainable throughput and therefore your goal is to identify the minimum amount of resources to maintain the throughput at a sufficient level, right? So my question is, since you consider a geographically distributed environment, the choice, how does the choice of throughput rather than latency can affect your goals of the autoscaling?
Okay. So your question is that okay.
So
Considering
why did you choose throughput rather than latency at the
okay,
beginning?
okay, yes, I got the point. Well, uh, well, okay. Well, I should say I should start with this point that the latency is first, it's more complicated, and because it's more difficult to having and proposing a model, and the model for latency and the model itself is more complex. But when we the question is that when we try model for I think the latency is better parameter when you are going to guarantee the real time in the system. I mean, you are going to guarantee that the processing time from the start to end of the system, be less than some values, and guaranteeing the real timeness of the. However, about the throughput, okay, our focus was on throughput because we are going to just show that, okay, to keep the system to process with the rate that the data is incoming. I mean, at the rate of the workload. To process the data at the rate of the workload is the objective of our objective to choosing the throughput. And in this way, if you keep the throughput as an ideal point, then it means that your system with the current configuration can process data, the incoming workload, at the rate of its incoming without queuing the unprocessed data. Because as soon as we queued the data, so it means that first we lost velocity. Why? Because it's just get our back to somehow we can say that it gets us back to the batch processing paradigm, because in where you put data in queue, it means that you store data and then process it. So we tried to keep the system as a stream processing system, and removing and skipping to putting data in a queue, and it means that we need to process data at the rate that it's coming. So for this reason, we select throughput. And of course, it will also reduce the complexity of the performance modeling, and auto scaling is easier than the latency, of course.
Yeah, and of course, it's also in line now with the choice of Flink, because Flink is a framework that optimizes throughput rather than latency for
Yes.
your experimental studies. So thanks. So my second question is about the performance model that you presented, which is based on an empirical methodology. And I would like to know if you have experienced the back pressure mechanism during the setting of your model. You discuss in your thesis the back pressure mechanism. And so I would like to know if you had the situation in which the back pressure mechanism is inactive. That means that the current operator that you are considering is overloaded, and so it cannot process the records at the same rate as they are received. And so you slow down that operator, and eventually the source operator or directly the sources that send records to that overloaded operator.
Okay, yes. Okay, so let me rephrase the question. So your question is that how we do this, how we monitor the back pressure, and what is the mechanism that we or the scenario that we follow based on the back pressure? This it was your question?
Yeah, if you when you perform your experiments for building the performance model, if
Okay.
you experienced the back pressure mechanism in act, because of course it depends on the arrival rate that you used in your experiments.
Okay. Yes. Ah. Okay. Let me. So yes, let me. I have a backup slide here. Let me. Oh yes, this one. Okay, and this is what actually it is the overload situation and the Flink's behavior in this because yes, as you mentioned, we use an Apache Flink. So in some cases like this, actually we need to choose a mechanism, and you need to follow a mechanism that Flink follows, or it's based on the behavior of Flink. So the back pressure is one of them. I think the monitoring the back pressure. And here I mentioned I describe a different states of the system, and you can see in the first stage the system works correctly and everything is okay. The incoming workload is as much as the two operators here, operator I minus one, and I can process it. So everything is okay. But in the second stage, the incoming workload will increase. So operator I minus one still can process it and it tune its throughput based on the increasing of the workload, incoming workload. However, the operator I cannot process with this rate, the incoming data with this rate. So it's just processed at the previous rate, and operator I minus one start to buffering the unsent data to the operator I. It start to buffering. And at some point, that buffer will be full, so it now start to triggering a back pressure, and it means that signaling a back pressure. It means that it first starts to slowing down itself, and then upstream operators and propagating this back pressure to the source. And here in this point, the throughput of the operator I is the maximum sustainable throughput. We call it the maximum sustainable throughput of operator I. And yes, here showing back pressure, and the presence of back pressure is on operator I minus one, but the reason of the back pressure is operator I. And is operator I is that that operator that already reached its maximum sustainable throughput and cannot process data faster. So if we are going to increase, so rescale the system, we need to increase the processing capacity of operator I. And we have this a maximum sustainable throughput here. So for actually the performance modeling, the measurements with is exactly when I talk about the measurements for having the performance and calibrating the model means these situations. You know, we can say that okay, we can have two different strategies. The first strategy is that okay, at the beginning of the application, before starting to process the real data from ingesting the real data, just send some artificial data to the system to make some back pressures in the system and then have measurements. It can be a first strategy, and the second strategy could be no, start the processing of the main data, and as soon as you have a back pressure, start to measurements and start to calibrating the model. This is the second measurements. We followed both of them, but finally we decided on the second one. run the system is working correctly, and as soon as we have the back pressure, the first back pressure, so we have the first measurement for the performance model, and then we have the first version, and so on, to more measurements. Yeah.
Okay, thanks. Thanks for the clear explanation. And now, did you measure the back pressure occurrence on the preceding operator?
After changing its capacity, you mean?
Mm-hmm. Yeah.
You mean after the configuration of the system, again monitoring the back?
Yeah, after, yeah.
Yes, of course. Every time that we change the reconfiguration, the configuration and reconfigure the system, we again restart or resume the process, the Flink, to process the application again, to process the data again. And yes, again, we regularly monitor the system, regularly monitor the different metrics.
Mm-hmm.
One of them, back pressure again. Yes, and the back pressure, but in parentheses, I should say that the back pressure is a parameter that Flink provides for us, and we just monitor it, and we consider some threshold for it to yes, determine it as a high back pressure or not. That's it.
Yeah, but because I remember that at some point in your thesis, maybe around page 50, you mentioned that there is a back pressure threshold, and you set it around 0.5. The back pressure value is between 0 and 1.
Yes. Okay. So your question is why we consider it? Yeah. Okay. Yes, actually, the back pressure mechanism of Flink works like this. It's a regular. You have a time interval that you set in the Flink configuration file, and it's a time interval between each running back pressure mechanism, and when you set it, for example, in 1 minute, in every minute, Flink send from the source, send some special streams, data sets, streams, and monitor those streams and the rate of and the time of getting and receiving those data in sync. And based on those special streams, Flink calculate the back pressure, and the back pressure value is between 0 and 1, and we considered it, and also the Flink client component also shows the back pressure as high when its value is more than 0.5. Yes.
Okay, I see.
At the high back pressure, yes.
Okay, thanks. So, and as regards the second contribution, so your Jscale system, when you scale out an operator, where do you place replicas of that operator? Do you leave the placement choice to Kubernetes?
Oh, okay. So your question is that, okay, in rescaling, in auto-scaling system, every time that we increase the number of replicas, so the new replica, we need to choose the place of the new replica. Okay. Yes, actually, it's a good question. Actually, I should say that yes, the placement is part of actually, I can say the scheduling. The scheduling is part of our work. I mentioned, I think, in one of the figures that we have a scheduling mechanism. Yes, here. So in the system design of Jscale, I mentioned that we have a resource controller component in Jscale, and the resource controller knows continuously and has up-to-date information about the available resources and the network latencies of of every. Okay, so we have a matrix of latencies, and based on the operator that you're going to increase its replicas, the resource controller just provides that available resources, and then in Kubernetes we customize the Kubernetes scheduler based on this three-step method. We didn't use we don't use the Kubernetes default scheduler for our own. We have our own scheduler, and in our scheduler, we have first the available nodes that are provided by the resource controller. And then we do a filtering process on them, and this filtering use some affinity and anti-affinity mechanism in Kubernetes, and based on, for example, we have some policies here. For example, to make it less complex, we run each replica on one pod separately, and we deploy a pod with one TM, task managers, and then one replica. So these kind of policies can be applied to the available nodes in filtering state. And then we have some remaining nodes after filtering. And now, based on the network latencies, based on that matrix that we have, we score the remaining nodes. And we sort the list of remaining nodes. And now, for example, in this example, you can see that N6 or node number 6 is our choice based on the first filtering and then scoring. And now we select the first node in the list, in the sorted list. So in this way, yes, we have our own scheduler, and then we trigger to Kubernetes to run new pod, to deploy new pod, which is contained of the new replica into the node number 6, for example, in this example. Yes.
Okay, thanks. So you have an additional monitoring component to measure the network latency
yes, I mentioned
among the nodes.
Let me show yes, this one. Here you see in the bottom layer, we have in Jscale, we also have in the left, we have a resource controller. And this resource controller does this kind of the resource management and controlling, and then providing the list for kubectl or for Kubernetes. Yes. And this.
Okay, thanks. And then I've just one curiosity, because in your experiments you used the New York taxi data trace, which is of course a good choice because it's representative of typical edge generated events which are processed by a distributed data stream processing system. But in a work we did with my research group last year, we noticed that this trace has a low variability in the data arrival rate. That means you don't have a bursty workload. You have some variability, but you don't have a high variability in the data arrival rate. So my curiosity is if you tried with a different data trace also for the experiment.
No, actually, Actually, yes, we used some artificial data in our experiments, but mainly for getting the evaluation results and comparing the autoscalers together, we used this workload. However, we added some, I think at the beginning, yes, in the first chart, you can see, but you told me that you had some experiences. So I think you have seen this chart, and this chart is the number of taxi rides during a day, one day. And so, yes, you can see the variety of the load of the number of taxi rides. And this is, yes, I mentioned, this is for one day. So we use it 3 days. And then we, just make it faster. The speed of change the speed of ingestion to the system, make it faster. So yes, our variation is somehow based on everyday variation of the number of the load of the taxi rides. Yes.
Okay, thanks. So So thank you very much for the detailed responses. Thanks.
You're welcome.
Thank you, Valeria. So I'll now turn to the second examiner, who is Cédric Tedeschi. So Cédric, over to you. Do you want the mic?
Yes, we do. Maybe it's better for people far away. Okay. So can you go back to slide 35?
35.
Yes. So here, it explains your deployment for your experiment. Right? So here you used one Raspberry Pi cluster, right?
Yes.
A single one. And you have on the master node, you have Jscale, which basically takes all the decisions and then relies on Kubernetes to apply the decision.
Exactly.
So the context of your work is fog computing, and at the beginning you explained that you're going to deploy this kind of applications at the scale of a city, or why not even at the scale of continent, because you take the example of Europe. So if you were to enlarge a bit the scale of this experiment, how would you do it? I mean, would you connect several Raspberry Pi clusters together? How many Flink job managers would you have? How many Jscale instances would you have? Would they communicate together to take the decisions and so on?
Okay. Yeah. Thank you. So your question is mainly about the scaling scenarios and larger scale scenarios for the system and how we can deploy Jscale itself and also Flink and other things in a larger scale system. Okay, yeah, it's a good question. Thank you very much. Well, yes. First, I mentioned, I think Roma asked a question about the scale. I answered about it, and I mentioned why we decided to use Raspberry clusters. And of course, when we use Raspberry clusters, we can increase the number of nodes to 23, 30, but not more. It's a little bit difficult to providing this number of Raspberry Pis. But yes, of course, and for example here, I should mention that first, why we deployed like this, based on our experiments. In this Raspberry cluster and in this number of Raspberries, we decided to put Jscale and, for example, Flink client, and so on in the main and master node, or for example, deploy Prometheus, Grafana, and Mina.io in another one, is a choice. Or a job manager in only one job manager and in one separate node running the job manager, or a master deployment of Flink and so on. It's a choice, and we did this based on our experiments with this cluster, with specifically the Raspberry Pi clusters. And yes, for example, if we have a bigger system, a larger system, and more number of resources, so definitely we deploy Jscale in a separate worker node and separately, or Flink client and so on. So our choice is based on the infrastructure or based on the cluster that we had. But this is, I think, it's about our deployment. But one more dimension of the question, if I understood well, is about more general about the deployment of these kind of auto-scaling systems in a fog or these kind of heterogeneous networks. Yeah. So for this reason, I told you this is a good question, because we have seen that many works followed different approach. Mainly, some of them are centralized approach and try to control and manage everything in auto-scaling mechanisms, centralized, while some others works tried to do it in a decentralized manner. And yes, I believe that in many cases, the decentralized manner, especially for fog computing or geo-distributed infrastructures, because the infrastructure itself is decentralized and distributed. So using the decentralized approach can have more advantage for these environments. However, the point here is that it was not our focus, to be honest. I can't say this is a limitation of our work that we didn't focus on, or we didn't consider much more on the how we centralize or decentralize our work, our autoscaler. We just pick one of them and try to focus more on the performance monitoring, the performance modeling, and rescaling, auto-scaling itself, rather than the how we distributed the scaling decisions or managing the scaling in a distributed manner and these things. So yes, I believe we didn't do this first, but I believe it was our choice to focus on this part and this point of view.
Okay. So if I just tried to replicate, let's say you had two RPI clusters. If you have only two, let's say. Two Raspberry Pi clusters. Okay. What would be your deployment? You would still have one Jscale instance, and still one Flink. Okay.
Okay. Yes.
I don't know.
Okay. Yes. The question is clear. Yes. I told you in this implementation and this deployment. Yes. If we add one additional Raspberry Pi cluster, so we have only more task managers to the system. We still keep the let's say the management part as it is, and we just increase the number of available task managers to the systems. That's it.
Okay. Thank you. I have a second question about the model. So, to what extent your model is influenced by the fact that you have chosen Flink? Do you think that this performance model could still be valid if, for instance, you used Spark streaming? Would you keep the exact same model both for one operator and for the whole workflow?
Okay. So I think it was. I can separate them to two questions. First, what if we use another DSP framework instead of Flink? And the second one was, I think you mentioned that. Can you rephrase the second part, because you mentioned that what if?
So you have one model for the performance of one operator, and you also showed that you have you showed how to extend the model to a complete workflow.
Okay.
And so when you switch from one DSP to another DSP framework to another one, would the model for one operator remain valid, and would the model still be valid for the whole workflow?
Okay. I got the question. It's now clear. Thanks. Okay. For the first part, well, yes, I would say yes. Actually, the selected parameters, as I described during the presentation, the selected parameters in the model are general for the frameworks. The parameters itself, network latency, number of replicas, or the parallelism factor of the system, and the parallelization inefficiency in the system, they are general. And in our development, I mentioned that we developed different tools. And in our development, we also considered it that probably later some users of this system will try to change, just keep the rest of the system as it is, and just change the DSP framework. So we tried to develop the tools as a modular system that not completely, but very easily you can change one module from the system. For example, you could change the Kubernetes, or you could change the DSP framework with some very small efforts. You can do it, because the model and also the parameter monitoring and those things in auto-scaling mechanism, we try to keep it as much as possible, keep it modular. So yes, I can say that with some efforts, you can change the DSP framework for the system, for both parts, for the performance modeling and also for auto-scaling. And for your second part of your question, I have a backup slide if I find it. Yes, here. Well, we have mentioned in our first contribution, I didn't mention in the presentation, but in the manuscript we have it. And here, in some of our experiments, we tried to model a full workflow. Well, we did several experiments with different objectives, and one of them was modeling an entire but simple workflow. And here you can see that we have a map operator, key value operator, and reduce operator. And each of them, for example, reduce has its own replication factor, and the map operator also has its own parallelism number. And so, yes, we tried to have some experimentations and show that the actually overall throughput and processing time of the workflow is limited to the slowest operator. In this case, you can see that the map operator, in the chart, you can see that the map operator has greater processing time. So the overall processing time of the workflow is somehow close to that operator. So we can say that, okay, the processing time of the workflow is equal to maximum processing time among the operators. Yes, but as I told you, we just had some experimentations with some small and simple workflows. Yes.
Okay, thank you very much.
You're welcome.
Thank you, Cedric. So I'll now turn to the PhD supervisors. I'm not sure who would like to start first. So maybe we can go by geographic distance once again and move to Umeå University. So Eric, Johan, maybe Eric, if you want to start with your questions.
Yeah, thank you very much. And as being in the role of a co-supervisor, I would like to decline the opportunity to ask questions today myself. But I anyway would like to take the opportunity to congratulate Hamid to having produced very nice thesis and strong papers in well-established venues. And also today I should tell that I appreciate the well-organized presentation that he delivered, and that he provided a very clear view of his main contributions of the 3 years of hard work. So congratulations to that part.
Thank you.
Thank you. So we'll now move to Johan. Johan, over to you.
Yes. So in the spirit of Eric, I think that the opportunity for the advisor to ask critical questions has been happening for many years now. So I would have no further question at this point, but would like to congratulate him to a nice pieces, and up until this point a very well performed defense as well. So I'll pass over the torch to Ren and Guillaume then.
Thank you. So I now turn to Guillaume. So Guillaume, the floor is yours.
So thanks a lot. Of course, I'm not going to ask any question. I just wanted to comment a bit about the journey that we went through together. I think that the defense today shows only part of what you have done over the last 3 years. Of course, you have done a lot of research on DSP frameworks, on performance modeling, on scaling, and I think we have had a lot of details about this work. But I wanted to mention the fact that this is only part of what Hamid has been doing over this time, considering that he has been a member of the Fog Group project. And the Fog Group project has actually given you a lot of other things. Of course, there was trainings, and you became a professional businessman thanks to innovation, entrepreneurship trainings. And one of the very important things in the project is that you've learned how to migrate between European countries. So you've done your work in Rennes, in Umeå, in Valencia, and moving multiple times between those places. And in doing this, you just happens to have participated in building a complete fog computing platform in Valencia. And I think you also became one of our best specialists in immigration legislations. In particular, your knowledge of the Spanish regulations is impressive. And I know you're building that knowledge about French regulations at the moment. When I think about the journey, when I think about everything you went through, there's one thing that I'm very proud, because I believe that we have taught you something important. In the beginning of your thesis, okay, you were enthusiastic, you were hardworking, you discovered things, but at the same time, I don't know, the uncertainty of research actually frightened you. So the idea that you were going to do something without knowing what the outcome is going to be, just because nobody else has done it before. And I think that over the time, you built up confidence in your own skills, and you've built up confidence that it doesn't matter whether we actually find what we expected or if we come up with something else. So this is something, I think that's probably the most precious thing that I think we have taught you. And this is something we'll keep for the rest of your life. So congratulations, and I'll give the mic back to François.
Thank you.
Thank you, Guillaume. So you've been asked many questions, so I won't ask many, but just maybe one first tiny question out of curiosity. So on the graph you're showing here, you've got error bars, and on most of your graphs too. So this is very nice, because this shows that experimental data has some distribution, and that you have to take into account this variability. But what surprises me a little bit about some error bars don't contain the actual point that you're using for the line. So could you tell us a little bit about the meaning of the error bars, and what some points are not within the error bars?
Yeah, sure. Yes, the question is clear. Well, yeah, good point actually. Well, first, there are two approaches for putting the error bar. Some time based on different calculations. For example, add, 5% errors for any measurement. But here we did several experimentations. We had several measurements, and we used it. If I remember well, for this one, we used three measurements. And we chose the middle one, the second one, as the main chart, showing the chart itself, and the two others for showing the errors and the different other values for as the error bars, And but yes, the error bars comes from three different values, and we used one of them for drawing the line itself, two others for the error bars.
Okay. Well, maybe we can discuss that offline a little bit more. But and then my second and last question, which is more kind of a meta question, not a technical one. So Guillaume commented on the journey that you've made through this PhD, and the PhD is as much producing the manuscript and some research as a process, and a very important product of a PhD, which is sometimes forgotten about, is in fact the doctor, and it's you in a way. So if you were to start again this PhD today, but with the knowledge you've acquired through these years of research, what would you do differently?
Find a better supervisor.
Of course not. Okay, so yes, interesting question. Thank you. I have my current knowledge about my research problem or my experience, my current experience. I believe,
more your current experience on how research works,
yes,
and what to pay attention to, and how to organize yourself, and other things you've learned about the research process.
Yes, yes. Okay, yes, it's really interesting question. Well, actually, I believe, especially when you work under supervision of some professional supervisors, you learn after 3 years, and for in my case 3 years, you really learn how to do research itself. I mean, yes, we call ourselves as a researcher when we start our PhD because we do some research, but to being a real researcher and to learning how to do research, it's completely different, another story. I believe that during these 3 years, Guillaume especially tried to make a researcher for me, and thanks to his efforts and what really I experienced it in these 3 years, now I can say that, okay, from the beginning of the research, the studying and defining the research problems and findings and having some hypotheses and these ones, I can do these things first autonomously. I now have learned about how to manage them, which step need to be done and in which time, and these things. And second thing, how really you can manage your time to control what you're looking for, what you're studying, what you're experiencing, or some engineering works that is usual in doing the PhD research. Sometime if I get back to last 3 years, so sometime I spent a lot of time on not on the most important thing, on some side works and these things that, yes, I had some experiences from those things, from those works, but they were not my main job or my main thing that on that time I should work on it. So yes, I think the time management and how you spend your time on which task, on which work is the second important thing that I achieved in the last 3 years. So yes, I say that doing research autonomously and exactly on time, it's my achievement, yes.
Thanks a lot. So I think this concludes the session of questions. So the panel will now go into a retreat. I don't know if we stay in this room or
no. So we have a different room.
All right.
And so we have a different room for the people here in Rennes, and for the people online, you can disconnect from this telco, and you have a second link for deliberation. So we'll be there in like 5 minutes.
Okay, thank you.
See you there.
maybe I should move somewhere in front of the.
Yes, maybe it's better if you go to the laptop so they see.
We should see Hamid as well, no?
Yeah, so
Okay, so
we'll
do our best. Okay, so if you want to, so that's just we see. So Hamid, the panel has deliberated regarding your PhD work, and we've agreed that you have done high quality work in the area of data stream processing for platforms that are deployed in geographically distributed fog computing infrastructures. And this is an area which is rapidly growing and definitely of high importance for modern computer science. You've presented contributions that are both analytical and practical on this topic, including a model for a performance model for these fog platforms, and as well as Jscale, which is an auto-scaling framework adapted to this type of environment. So the jury appreciated the very pedagogical presentation that you were able to deliver. And we also noted that you were able to summarize the key insights and the motivation of your work. You've answered our many questions, and through your answers, you demonstrated that you had an excellent knowledge of your field, as well as a clear scientific mentality. One important thing that the jury would like to emphasize is the very substantial experimental work and developmental work that you performed. And the result of this software development work is also available to the wider community, which is quite important for future work that we build on your own contributions. And so for all these reasons, the jury decided to, was unanimous in deciding to award you the diploma of Doctor of the University of Belgium, specialty computer science. Congratulations.
So thank you very much for your positive opinion. I'm happy about it. I would like to use this opportunity to say thank you to everyone. Well, first of all, thank you, Romain and Laurent, for reviewing the manuscript and giving me valuable feedbacks. Thank you very much. And thank you, Valeria, and Cedric and Francois for attending my defense as the jury members. Thank you for your interesting question and nice discussions that we had. Thank you very much. I would like also to say thank you to my supervisors, Eric and Johan from Sweden, from latencies company, where I spent there several months there. And I enjoyed working with a very professional team and in a very nice and friendly environment. Thank you very much for everything. I would also say thank you to Guillaume, to my main supervisor. I worked under your supervision, in direct supervision, in the last 3.5 years. Well, Guillaume, no, I can't find a proper words to describe your continuous support and continuous care about me, about my thesis and my research. You know, Guillaume really helped me, really guided me about everything, from the early understanding the research problem to having contributions to even about the writing the thesis. He had very precise and helpful comments. And I can say that, Guillaume, you were not my supervisor. You were like my big brother. You helped me not only in a professional part of my life, but also in my personal part of my life. And I'm really honored for working under your supervision. And I really thank you for everything you did for me And I really hope I can pay forward what you have done for me by helping other people and guiding other people. Thank you so much. I would like also say thanks to my friends from Fog Grove Project and Mirios team. I enjoyed working and living with you in last 3 years, especially with Fog Grove Project. I spent a lot of time together. We spent together in Spain, in Sweden, and I really enjoyed working with you and living with you. And thank you very much, you all. I would like also say thank you to my Iranian friends who are here and who are not here, especially with thank you Jawad and Marzieh and Mohammed and his wife, and also Mujtaba and his wife who are not here. And I had a wonderful time with you in last 3 years. I would like to say thank you to my family, and especially to my parents. Well, they really like to be here, but it was not possible. Well, they always followed my progress and my achievements and always supported me. And well, I'm sure they are watching this video or will watch later. So I like to say that you always told me that we're proud of you, but now I like to say that I'm really proud of having you as my parents. Thank you very much. I would like to say thank you to my parents-in-law, my mother-in-law and my late father-in-law, who unfortunately we lost him last year. And I wish his soul rest in peace forever. And last one and the most important one, I would like to say thank you to my wife. She's here, Atefe, and she always has been by my side. And thank you for your support and accompanying me in this journey. I say that you are the only one. If you were not in my life, I could not even start this PhD. So thank you very much. I'm really grateful to have you in my life as my partner. Thank you very much. And that's it. Thank you very much. Thank you again, everybody. Thank you.
Congratulations.
Thank you.
Congratulations.
Thank you very much.
Congratulations, Hamid.
Congratulations. Well done.
So it's time to close the video session. Your punishment for not coming to Rennes is not having a taste of the wonderful drinks and snacks.
Yeah.
And Romain, we see each other this afternoon, right?
Yes.
Good.
It was good to see you all. Bye-bye.